A really brief video on the ambiguous case of the sine rule. Now this comes about because, as we know, sine is positive in the first and second quadrants. So sine of 120 degrees is the same as sine of 60 degrees, which means if you have the right size angles in a triangle, you could possibly get two potential answers for the unknown angle. All right, so in this case here, so looking at the triangle, we find the value of theta. So straight away, because we're finding an angle, we can say that sine of theta on the side that's opposite, which is 7 root 6, is equal to sine of 45 on 14. Now, I'm going to use the exact values because I suspect I might end up with an answer that I can come up with here. Now, sine of 45 is 1 on root 2, so let's just write those in. So sine theta, so sine 45, thinking of the special angle, 1 root 2. So sine 45 is 1 on root 2, so this will be 1 on root 2 times 7 on, times 7 root 6 on 14. I can already see this is going to be a special angle. And that becomes 7. Now root 6 on root 2 is root 3. So it's 7 root 6 on 14. Whoops, sorry, I'm really having trouble this morning. This is why I'm away sick, guys. So it's 7 root 6 on root 2, which is 7 root 3 on 14, which is root 3 on 2. Okay, and how did I know it was going to be a special angle? Because I had the sine 45 in there. So as I've said to you before, if you've got that, you're already always thinking to yourself, it's probably a special angle. Okay, so the root 3 on 2 I recognize as being one of the special triangles. We've got a 2, a root 3, and a 1. So it's this angle here, which is a 60 degrees. Wow, I didn't know it was a 60 degree one. So my two answers I could possibly get are theta is equal to 60 degrees, in which case the other angle at Q would be 75, or it's 120 degrees. Both those give the same answer, in which case the angle at theta at Q will be 120 plus 45 is 65, would be 15. So we actually get two answers here. So both of those answers are possible, and given the triangle we have, we cannot decide which one it would be. So the other triangle would look something like, now I'll just draw it in a different color. So we've got a 45 degree angle here. Oopsie daisy. So we still get a 45 degree angle. It's only the one at the top that's going to change to be like that, and 120 degrees. Or a 60 degree angle like the one that's there. In which case this one here will be 15, and this length here is the one that will change. Okay, if that length was fixed, we wouldn't have the ambiguous case. In fact, if that length was fixed, we'd have to use the cosine rule to find that angle. But this length down the bottom here, that can be either long or short. It doesn't necessarily, there's no information that tells us either way. Hence, both those angles can work. All right, we'll look at one more quick example on the ambiguous case of the sine rule. Whoops, why did I change that out? Okay, so in example 21, which is the one below. Okay, in triangle ABC, angle A is, I hate the way I've written that, angle A is 25 degrees, so let's just draw a triangle. Let's call this A here. So this is 25 degrees. BC is 9, and AB is 20 centimeters, okay? All right, find angle C. So this is the angle I want to find. All right, so just brute forcing it, sine theta on 20 is equal to sine 25 on 9, and no special angles this time. So sine theta would equal 20 times sine 25 divided by 9. And using our calculator again, with inverse sine, so inverse sine of, using the fractions button, 20 times Sine 25 divided by 9, close brackets, equals, and nearest degree, so it's 60.9, I'm going to break my rule, so 70 degrees. Okay, so theta is equal to 70 degrees. Now, the other alternative is that theta is 110 degrees, or 180 minus 70 degrees. So if theta was 110 degrees, then what does the triangle look like? Well, once again, we still don't know what AC looks like. All right, so it could be really, really long. So notice I've now drawn it a lot longer. So this AB still stays at 20. This one still stays at 9, except this angle up here, in the first triangle it's 70 degrees, which it kind of looks like it is, and this triangle it's 110 degrees. So you'll notice that it's this length down here I've labelled X is the one that's going to change. I'll just better label the vertices of that triangle so it makes it obvious to you. A, B, C. You can see that by stretching it out and bringing it down, I'm going to increase that angle even though I've kept the same side lengths. It will change the length of AC, but we weren't given that in the first case. So that's how we can get the ambiguous case. To get the 110 degrees, I did 180 minus 70 because in the first quadrant, 70 degrees, and in the second quadrant, it'll be 180 minus 70 degrees, which is 110 degrees up here like that. Hopefully that helps you with the ambiguous case. You just have to be careful if you're not given enough information. Sometimes in the question they'll tell you that the angle is acute or obtuse, and if it tells you that, obviously only one of the answers will work. Or if the other angles mean that it's going to add to more than 180 degrees. So say, for example, that angle down the bottom was, I don't know, something different that meant that I couldn't get a value less than 180 with another angle, then obviously the second case doesn't work either because the angle sum of a triangle is 180 degrees. Just be careful with the ambiguous case.